Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
A peculiar attention on the geometric imagination of the early 19th century. A new way of seeing space, projective geometry, was offering astonishing insights, unifying the disparate properties of circles, ellipses, parabolas, and hyperbolas into a single, elegant theory of conic sections. Its practitioners, figures like the brilliant French engineer Jean-Victor Poncelet, wielded powerful conceptual tools with an almost artistic flair. Yet, beneath the surface of this magnificent new structure, there was a tremor of logical uncertainty. The foundations felt provisional, borrowed, and, at times, unsettlingly intuitive. The discipline that for 2 millennia stood as the exemplar of rigorous deduction, Euclidean geometry, was now giving birth to a successor whose very power seemed to stem from a certain logical abandon. Poncelet, returning to France after his captivity in a Russian prison during the Napoleonic campaigns, brought with him a revolutionary idea he called the principle of continuity. The principle asserted, with breathtaking confidence, that a property proven for one geometric figure would hold for any other figure derived from it through a continuous transformation, even if the transformation passed through a degenerate or imaginary state. Consider 2 intersecting circles. They meet at 2 real points. As one circle is pulled away from the other, these 2 points of intersection draw closer, merge into a single point of tangency, and then vanish from the real plane entirely. For Poncelet, these points did away with their existence, they merely became imaginary. He continued to reason about them as if they were present, a pair of conjugate imaginary points residing somewhere in a complex extension of the plane. This method yielded correct results with remarkable efficiency. It allowed geometers to treat parallel lines as lines that meet at a point at infinity, unifying the concepts of intersection and parallelism. The problem was that these imaginary points and points at infinity had no rigorous definition. They were invoked, like helpful spirits, to preserve the generality of theorems. The entire system, for all its beauty, rested on an analogy. It was a geometry that depended on the metric concepts of Euclidean space, distance, angle, and measurement to get started, and then asked its audience to accept a leap of faith across a logical chasm. Into this environment of fertile discovery and foundational anxiety stepped Karl von Staudt, a quiet, meticulous professor at the University of Erlangen. Von Staudt was a figure whose temperament seemed perfectly suited to the task of bringing order to this beautiful chaos. His life was one of academic dedication, free of the romantic drama that characterized some of his contemporaries. His ambition was of a different sort, a purely intellectual quest for absolute logical purity in geometry. He looked upon the work of his predecessors and saw both its genius and its Achilles heel. He recognized that the power of projective geometry came from its focus on properties that are invariant under projection, properties like collinearity of points and concurrency of lines. He also saw that its dependence on metric ideas was a conceptual impurity, a vestige of an older way of thinking that prevented the field from standing on its own feet. His response was the publication in 1047 of his magnum opus, Geometrie der Lage, or Geometry of Position. The title itself is a declaration of intent. This would be a geometry concerned exclusively with position or situation, a science of pure relation. All concepts of magnitude, of length, of angle, of congruence were to be systematically excised. The work begins with an austere set of axioms concerning only points, lines, and planes, and their one fundamental relationship, incidence. A point lies on a line passes to a point. From this starkly simple foundation, von Staudt proposed to reconstruct the entirety of projective geometry. His tools were the mind and an unmarked straightedge. The compass, the ancient instrument of measurement, was banished. The Cartesian coordinate system, which defines points using numerical distances from axes, was likewise forbidden as a foundational tool. He sought to demonstrate that the whole rich tapestry of projective theorems could be woven from the single thread of incidence. In this ambitious project, von Staudt was responding directly to the towering figures who preceded him. He deeply admired the work of the Swiss geometer Jacob Steiner, a master of synthetic geometry who could produce dazzlingly complex constructions using a straightedge alone. Steiner's work represented a high point of geometric intuition, a celebration of visual and spatial reasoning. Yet, even Steiner's proofs often contained unstated assumptions rooted in our Euclidean intuition of space. When Steiner proved that any construction possible with a compass and straightedge is possible with a straightedge alone given a single fixed circle, he was still operating within a world where a circle was a metric object defined by a center and a radius. Von Staudt absorbed Steiner's commitment to synthetic methods while seeking to ground them in a more rigorous, non-metric logic. From Poncelet, he took the grand scope and the central problems of projective geometry. He embraced the unifying power of concepts like the point at infinity and the complexification of the plane. His goal, however, was to give these ideas a formal, rigorous definition derived from within the projective system itself. Where Poncelet had made an intuitive leap, von Staudt would build a logical bridge. He would show how to define these ideal elements using only the real, finite points and lines of the plane. An imaginary point in von Staudt's system would be defined as a specific type of geometric transformation and involution without real fixed points, a concept built entirely from the axioms of incidence. The key to this entire enterprise, the fulcrum upon which his new geometry would turn, was a concept he called the werf, a term most closely translated as a throw or cast. A throw is an ordered set of 4 collinear points. Let us call them A, B, C, and D. To the casual observer, this is an unremarkable configuration. For von Staudt, it was the atom of projective measurement. He discovered that within the relationships of these 4 points, governed by constructions involving only a straightedge, lay the deep structure of arithmetic. He would demonstrate that one could define operations corresponding to addition and multiplication on the points of a line. The identity element for addition, the point 0, and the identity for multiplication, the point 1, could be designated. The entire algebraic field of numbers, he would prove, was an intrinsic consequence of the axioms of projective geometry. The numbers were already there, latent in the relationships of incidence, waiting to be revealed. This was a profound and revolutionary insight. It established that projective geometry was a completely autonomous discipline. It required no support from Euclidean metrics or Cartesian algebra to establish its logical coherence. In fact, the relationship was the other way around. The fundamental properties of our number systems could be seen as emerging from the even more fundamental properties of spatial arrangement. Von Staudt's geometry der Lage provided the definitive answer to the foundational questions of his time. It secured the logical bedrock of the field, transforming it from a collection of powerful techniques into a self-contained and rigorous mathematical theory. The question that his work immediately posed to the world was as astonishing as its conclusion. How can the simple act of drawing lines through points, of casting a throw upon a line, possibly give rise to the familiar operations of adding and multiplying numbers? The answer lies in his ingenious calculus of throws, a mechanism of pure logic that builds an algebraic world from the sparest of geometric materials. The architecture of this new geometry, erected upon the sparest axioms of incidence, presented a profound intellectual puzzle. If the universe of projective geometry contains only points, lines, and their connections, how could one possibly replicate the familiar world of arithmetic? The challenge was to define operations like addition and multiplication for points on a line using a straight edge alone, without any reference to distance, angle, or pre-existing number system. Karl von Staudt's answer, the centerpiece of his 1847 masterpiece, Geometry der Lage, was a construction of breathtaking ingenuity known as the calculus of throws, or Calcul der Wurf. This was the engine that would generate a complete algebraic field from the elemental dust of geometric relations. The foundational concept, the very first gear in this intricate logical machine, is the harmonic conjugate. Given three distinct points on a line, let us call them A, B, and C. Projective geometry provides a canonical method for finding a unique fourth point, D, which stands in a special relationship to the first three. This relationship is harmonic separation. To construct this point D, von Staudt employed a figure known as a complete quadrangle. Imagine any 4 points in the plane, with the condition that no 3 lie on the same line. These 4 points determine 6 connecting lines. Now, consider a line passing through one of our initial points, say C, but avoiding A and B. We select 2 of the quadrangle's vertices, let's call them P and Q, to lie on this line. The remaining 2 vertices, R and S, lie off the line. We draw the lines connecting P to A and Q to B. Their intersection defines a new point, M. Then we draw the lines connecting P to B and Q to A. Their intersection defines another new point, N. The crucial step is the final one, the line passing through M and N will intersect our original line containing A, B, and C at precisely the sought-after fourth point, D. This construction is remarkable for its purity. It uses only the incidence of points and lines. The resulting point D is the harmonic conjugate of C with respect to A and B. The set of 4 points A, B, C, and D forms a harmonic range. What von Staudt established was that this construction always yields the same point D, regardless of which complete quadrangle is used, as long as the initial setup is maintained. This invariance provided the stability needed for a formal system. He had found a purely geometric relationship that was as robust and unambiguous as any algebraic equation. This harmonic relationship would serve as the cornerstone for defining arithmetic. For instance, if we designate one point on the line as the origin, 0, and another as the point at infinity, then the harmonic conjugate of the point 1 is -1. A primitive form of algebraic structure was beginning to emerge from these straight-edge constructions. With this harmonic foundation in place, von Staudt proceeded to define the operations of addition and multiplication. To achieve this, he first designated 3 special points on a line, which he labeled 0, 1, and infinity. These serve as the reference frame for the entire arithmetic. The choice is arbitrary, yet once made, the entire algebraic structure is fixed. To define the sum of 2 points, x and y, he devised another elegant construction. Take 2 lines intersecting at the point designated as infinity. On the first line, mark the points 0, 1, x, and y. Through the point 0, draw a third line. Now, using an auxiliary point in the plane, project the points from the first line onto the third line. Then, using a second auxiliary point, cleverly chosen in relation to the first, project the points back onto the second line. The geometry of this sequence of projections, governed by the properties of perspectivity, ensures that the resulting point on the second line corresponds to the sum x plus y. The procedure, while intricate to describe, flows from a few elementary principles and again relies solely on incidence, is associative and commutative. X plus y is the same as y plus x. An entire group structure for addition had been summoned into existence. The definition of multiplication was even more profound, requiring a deeper result from classical geometry, the theorem of Pappus of Alexandria. To construct the product of 2 points, x and y, von Staudt again begins with 2 lines intersecting, this time at the point designated as 0. On the first line, he marks the points 1 and y. On the second line, he marks the point x. Now, he invokes Pappus's hexagon theorem. He selects an arbitrary line passing through the point 1. The intersection of this line with a line containing x defines a point, and its intersection with a line drawn from y to the point at infinity defines another. The 6 points in this configuration, 1, y, infinity on the first line, and 0, x, and another point on the second form the vertices of the hexagon whose sides alternately lie on the 2 initial lines. Pappus's theorem guarantees that the 3 intersection points of opposite sides of this hexagon are collinear. Von Staudt's genius was to arrange the construction so that this very line of collinearity would pass to the point representing the product, x times y, on the first line. This construction was a masterstroke. It demonstrated that the multiplicative structure of a field was also inherent in the projective plane's axioms. The properties of associativity, commutativity, and distributivity of multiplication over addition could all be proven as geometric theorems flowing from this construction and the properties of projectivities. The entire ethos of a field, equivalent to the field of real numbers, could be built from the ground up. This achievement had staggering implications. It showed that the algebraic properties of numbers were reflections of geometric configurations. The laws of arithmetic were consequences of the laws of spatial arrangement. It was Felix Klein, in his celebrated 172 Erlang engine program, fully grasped and articulated the revolutionary nature of von Staudt's work. Klein recognized that von Staudt had successfully decoupled geometry from its traditional reliance on metric and analytic concepts. Geometry, in Klein's view, is the study of invariance under a group of transformations. Von Staudt had analyzed the most fundamental group, the projective group, and had shown that an entire algebraic field field structure was one of its invariants. This provided a powerful new way to classify geometries. Euclidean geometry could now be understood as a subgeometry of projective geometry, one in which a particular conic section, the absolute conic, is held invariant, giving rise to our familiar notions of distance and angle. Von Staudt's calculus of throws was a mechanism that proved this hierarchical relationship was logically sound. It provided the rigorous foundation for Klein's visionary synthesis of geometry and group theory. Having forged a complete algebra from the raw material of incidence, von Staudt possessed a new analytical engine. The next logical target for this powerful synthetic machinery was a family of curves that had fascinated geometers since antiquity, the conic sections. Having forged a complete algebra from the raw material of incidence, von Staudt possessed a new analytical engine. The next logical target for this powerful synthetic machinery was a family of curves that had fascinated geometers since antiquity, the conic sections. His ambition was to reconstruct the entire theory of ellipses, parabolas, and hyperbolas using exclusively the austere language of projective geometry. The familiar definitions rooted in measurement distances, foci, ratios of eccentricity, perpendiculars to a directrix, were to be completely abandoned. In their place, von Staudt sought a foundation built upon the relationships between points and lines alone, a geometry of pure position. The problem was one of liberation to free the conic from the tyranny of the ruler and protractor and to reveal its essential, unadorned form. The initial spark for this endeavor came from his contemporary, the Swiss geometer Jakob Steiner. Steiner, a master of intuitive geometric construction, had proposed a breathtakingly elegant way to generate a conic. One begins with 2 points in the plane. Let us call them V1 and V2. Imagine 2 pencils of lines, one rotating around V1 and the other around V2. Now, establish a projective correspondence between the lines of the first pencil and the lines of the second. This means for every line passing through V1, there is a unique corresponding line passing through V2. And this correspondence preserves the cross ratio. The locus of all intersection points of corresponding lines, Steiner demonstrated, traces out a conic section passing through V1 and V2. This was a dynamic, generative definition of profound beauty. It produced an ellipse, a parabola, or a hyperbola based entirely on the nature of the projectivity established between the 2 pencils. For Steiner, this was a principle of discovery, a tool for generating beautiful results. For von Staudt, it was something that was a candidate for a rigorous axiomatic starting point, an idea that could be systematized and made the logical cornerstone of a complete theory. Von Staudt's genius lay in transforming Steiner's constructive insight into a formal, analytical framework. He achieved this through the systematic development of one of projective geometry's most powerful and subtle concepts, the polarity. A polarity, with respect to a given conic, is a transformative correspondence that permeates the entire projective plane. It assigns to every point in the plane a unique line, called its polar. Conversely, it assigns to every line in the plane a unique point, called its pole. This is a perfect duality. The pole of a polar line is the original point. The polar of a pole is the original line. This relationship provides a way to talk about the conic's influence on the entire space it inhabits. The true elegance of this concept becomes apparent through concrete application. Consider the classical problem of constructing the tangent to a conic at a given point P. Using metric geometry, one might employ derivatives or complex constructions involving foci. Within von Staudt's framework, the solution is astonishingly direct. If the point P lies on the conic itself, its polar line is, by definition, the tangent to the conic at P. The construction requires only a straight edge. For a point Q lying outside the conic, its polar line is the chord connecting the 2 points of tangency to the lines drawn from Q to the conic. The polarity thus encodes all the tangential properties of the curve into a universal mapping of points to lines. With this tool in hand, von Staudt could offer a definition of the conic of unparalleled abstract purity. A conic section, he proposed, is the set of all self-conjugate points in a polarity. It is the locus of points that lie upon their own polar lines. This definition is completely self-contained. It makes reference to anything outside the system of points, lines, and the polarity transformation itself. The conic becomes a fixed structure, a geometric invariant, defined by its own internal duality. From this single definition, all properties of conics could be derived synthetically. The distinction between ellipse, parabola, and hyperbola emerges from how the polarity interacts with the line at infinity, whether the polar of a point at infinity is a finite line, or whether the conic contains points at infinity itself. All of this is determined without a single measurement of length or angle. This framework also solidified a fundamental principle of projective geometry concerning conic. While in Euclidean geometry it famously takes 5 general points to uniquely determine a conic, von Staudt's work clarified the projective equivalent. This formulation, building on the work of Mitchell-Chasles, showed that a projectivity between the points on 2 lines is uniquely determined by 3 pairs of corresponding points. Since a conic could be generated by such a projectivity, this implied that the projective nature of a conic was locked in by a very small amount of initial information. This principle became the cornerstone for the classification and study of curves within the new geometry. The impact of this rigorous, synthetic treatment of conics was immediate and profound, particularly within the nascent Italian school of algebraic geometry. Luigi Cremona, a brilliant geometer and later a statesman of the unified Italy, saw in von Staudt's work a blueprint for a grander program. Cremona absorbed the methods of polarity and projective correspondence and began applying them to curves of higher degree and to geometric transformations between surfaces. The famous Cremona transformations were rational maps between projective planes or direct intellectual descendants of the projectivities that von Staudt had placed at the heart of geometry. Cremona and his followers, including Corrado Seger and Guido Castigliovo, championed this synthetic, visual approach. They built a rich, complex world of algebraic geometry grounded in the rigorous, coordinate-free foundations that von Staudt had so painstakingly laid, while the German school, following mathematicians like Alfred Clebsch, increasingly leaned on algebraic formulas. The Italian school carried the torch of pure synthetic reasoning, a flame lit by the clarity of von Staudt's vision. Through this monumental effort, von Staudt had taken one of the most ancient subjects in mathematics and recast it in a form that was startlingly modern. He had demonstrated that his calculus of throws was a tool capable of rebuilding classical geometry from first principles. The world of conics, once described by a pantheon of Greek terms related to cutting cones, was now understood as a manifestation of a single, unifying projective principle. Yet, this purified real projective plane, for all its perfection, had a limitation. It was complete. Yet it was unable to account for the persistent and useful specters of imaginary numbers that appeared in algebraic solutions. A circle and a line that failed to intersect in the real plane were said by algebraists to meet at two imaginary points. For a synthetic geometer like von Staudt, such a statement was meaningless without a concrete geometric object to represent it. The next, and perhaps most audacious, step in his intellectual journey would be to construct these phantoms from the solid ground of real geometry itself. The intellectual edifice of the real projective plane, which von Staudt had constructed with such austere elegance, stood as a testament to the power of pure reason. Within its framework, the calculus of throws provided a complete arithmetic, and the principle of projective generation gave a unified theory of conic sections. Yet, for all its internal consistency, this world remained haunted by phantoms from another realm, the realm of algebra. When a geometer considered a circle and a line that remained separate in the plane, their analysis concluded with a simple statement of fact. An algebraist, however, describing the same scenario with equations, would discover two solutions for their intersection points, solutions containing that peculiar entity, the square root of a negative number. These were the imaginary points whose existence Jean-Victor Poncelet had posited with his powerful, albeit unproven, principle of continuity. For Poncelet, they were a matter of conceptual necessity, a way to preserve the generality of geometric theorems. For von Staudt, this was an unacceptable state of affairs. A geometric statement required a geometric object. His final and most audacious work, the three-volume Batrich zur Geometrie der Lage published between Vaides et 6 and Vaides et 60, would be his answer. It is a campaign to capture these algebraic ghosts and give them body and form within the tangible world of synthetic geometry. The central crisis was one of representation. How could one construct a thing whose defining characteristic was its failure to appear in real space? Consider the problem in its most concrete form. A circle C and a line L lie in a plane without meeting. The corresponding quadratic equation yields two routes for the intersection, which we might write as P and P bar, a complex conjugate pair. These points have coordinates, but the coordinates involve the imaginary unit I. They lack a position a compass and straight edge could ever locate. Poncelet's principle suggested that if one were to move the line L until it touched the circle, the two real intersection points would merge into one, and as the line moved away again, they would split into a pair of imaginary points. This intuitive picture was compelling, a beautiful narrative of continuity. It was also, from a logical perspective, an appeal to faith. It offered a story about how imaginary points behave, while providing absolutely no definition of what the asterisk or asterisk. Von Staudt's objective was to replace this narrative with a definition to build an object out of the real points and lines of his existing geometry that would have all the required properties of a complex conjugate pair. His solution is one of the most profound acts of conceptual creativity in the history of mathematics. He turned his attention away from the search for a static point and instead focused on a dynamic relationship on the line L. He considered a special kind of projective transformation on the line known as an involution. An involution is a mapping that, when applied twice, returns every point to its original position. It pairs up the points on the line if the involution maps it to B. It must also map B to A. On a real line, these involutions come in two distinct flavors. A hyperbolic involution possesses two real fixed points, two locations that are mapped onto themselves. An elliptic involution, by contrast, possesses the remarkable property of having zero real fixed points. It relentlessly shuffles every point on the line to a new location. Here was von Staudt's masterstroke. He proposed that a pair of complex conjugate points on a real line asterisk is asterisk an elliptic involution on that line. The geometric object is the mapping itself. The elusiveness of the imaginary points was perfectly captured by the character of the elliptic involution, which fixes nothing in the real domain. It found the ghost in the machine. To see how this works, we return to the circle C and the non-intersecting line L. Using the established projective theory of poles and polars with respect to the circle, von Staudt could construct a unique involution on the line L. For any point P on L, its polar is a line that passes through the center of the circle. The point P prime where this polar intersects L is the image of P under the involution. This construction, performed for all points on L, generates a perfect elliptic involution. This mapping, this systematic pairing of all points on the line L according to a rule dictated by the circle C, became von Staudt's rigorous, synthetically constructed representation of the two imaginary points of intersection. This was a radical conceptual leap. A geometric element, traditionally a static entity like a point or a line, was now identified with a transformation. But its power lay in its consistency and extensibility. Having defined an imaginary point, von Staudt proceeded to build an entire, complex geometry upon this foundation. An imaginary line, for instance, could be defined. An imaginary point in the plane, being an elliptic involution on a real line, is determined by three pairs of corresponding points. A real point in the plane is determined by the pencil of all lines passing through it. An imaginary line was therefore defined as a set of connections between corresponding points of two projective pencils of lines whose centers are real, but whose projectivity has imaginary fixed race. He demonstrated that his calculus of throws could be generalized to operate on these new complex elements. One could calculate the cross ratio of four imaginary points on a line, defined in terms of their corresponding involutions. This allowed the whole machinery of projective invariance to be deployed in the complex domain. The theory reached its apex with a geometric construction of the most famous imaginary entities of all the circular points at infinity, often labeled I and J. In algebraic geometry, these are the two special points on the line at infinity through which every circle in the plane passes. For von Staudt, this algebraic curiosity became a concrete geometric structure. He defined a specific elliptic involution on the line at infinity, the absolute involution, where pairs of directions are orthogonal. This very involution asterisk is asterisk the pair of circular points I and J. A circle could then be defined projectively as any conic that passes through these 2 points, that is, any conic that cuts the line at infinity in the pairs of the absolute involution. This single, powerful definition unified the theory of circles with the general theory of conics in a way that was both completely rigorous and purely geometric. The immediate impact of the Batrich asterisk was profound, particularly on the next generation of geometers who were seeking to place the field on the most secure logical footing. Felix Klein, in formulating his celebrated Erlangen program in 1772, drew immense inspiration from von Staudt's work. Klein's idea to classify geometries by the groups of transformations under which the properties remain invariant required a clear understanding of the geometric space and the elements within it. Von Staudt's construction of the complex projective plane provided a perfect, unified arena where the transformation groups of projective, affine, and Euclidean geometry could be seen as a nested hierarchy. The ability to handle real and complex elements seamlessly within a single synthetic framework was a critical prerequisite for Klein's vision. Similarly, the Italian school of axiomatic geometers, most notably Mario Piri, saw in von Staudt's work the blueprint for a geometry built from minimal assumptions, where even the complex number system itself could emerge from axioms of incidence and order. By giving geometric substance to the imaginary, von Staudt had accomplished something of immense significance. He had taken the last piece of algebraic machinery that seemed foreign to pure geometry and had shown it to be a native citizen of the projected world. The complex projective plane was revealed as a truly complete and natural environment for geometry, a space where two distinct conics always intersect in 4 points, real or imaginary, and where theorems held with a beautiful, exceptionless generality. This final, heroic construction did more than solve a technical problem. It prepared the ground for a fundamental reevaluation of the nature of geometry itself, demonstrating that its truths were dependent, ultimately, only on the logical coherence of abstract relational structures. The successful integration of complex elements into the projective plane provided the final piece for a revolutionary thesis about the very identity of geometry. With his system complete, Karl von Staudt had fashioned an entire world from the sparest of materials. The edifice of projective geometry, including its most subtle features like conic sections and imaginary points, now stood firm upon a foundation containing exclusively axioms of incidence statements about which points lie on which lines. Concepts like distance, angle, length, and congruence, the traditional bedrock of geometric reasoning since Euclid, were entirely absent. They were revealed as useful, powerful, yet ultimately secondary properties, specializations of a more general and fundamental truth. This achievement amounted to a profound recharacterization of the discipline. Geometry, in the Staudtian view, was the science of pure relation, of abstract structure defined by commutativity. The physical space of human intuition, with its rigid motions and measurements, became one possible interpretation of a far grander, more abstract system. This radical reconception of geometry's core principles resonated powerfully through the subsequent decades, providing essential groundwork for one of the most unifying concepts in modern mathematics. Felix Klein's Error Engine program, presented in 1972. A mere 5 years after von Staudt's death, Klein's program proposed that a geometry could be defined by a space and a group of transformations acting on that space. The properties of the geometry are precisely those features that remain invariant under the transformations of its associated group. For Euclidean geometry, the group is the set of rigid motions, translations, rotations, reflections, and the invariants are distance and angle. For von Staudt's projective geometry, the group is the set of all projected transformations, the colligations, and the supreme invariant is the cross ratio. Von Staudt had, in effect, constructed the very object that Klein's program would later classify. He had built a complete geometry by implicitly working with its invariants, demonstrating that the entire structure could be derived from the preservation of collinearity and the algebraic properties of the cross ratio. Klein's genius was to recognize this principle as a universal organizing key for all geometries. He saw that von Staudt's work was the ultimate proof of concept. It showed that a rich, consistent, and comprehensive geometry could exist whose primary features were those unchanged by projection and section. The Error Engine program gave von Staudt's achievement its modern language and context, placing it at the head of a hierarchy. Projective geometry, being defined by the most general group of transformations, became the parent from which other, more restrictive geometries could be derived. To get to affine geometry, one singles out a line at infinity. To get to Euclidean geometry, one adds a metric structure to that affine plane, defining a specific imaginary circle on the line at infinity. Von Staudt built the universal cathedral. Klein provided the guidebook explaining its architecture and its relationship to all the smaller chapels in the city of geometry. The philosophical purity of von Staudt's approach its construction of a complex system from the fewest possible assumptions also blazed a trail for the great axiomatic projects of the late 19th and early 20th centuries. His insistence on a development free from appeals to spatial intuition became a guiding principle for figures like Morris Pesch. In his 182 work, Volksungen über nur Geometrie Pesch explicitly sought to formalize the implicit assumptions within geometry, such as the axiom of order, which states that a line entering a triangle must also exit it. This drive toward logical transparency and the elimination of unstated premises is a direct intellectual inheritance from von Staudt. This influence is perhaps even more pronounced in the work of the Italian school of geometers, particularly Mario Piri. Piri, a collaborator of Giuseppe Pino, took von Staudt's minimalism to its logical extreme. In his 1899 treatise on the foundations of projective geometry, Piri demonstrated that the entire subject could be developed from two undefined terms, point, and line, and a set of axioms governing their incidence. His system was a marvel of logical economy, a testament to the power of the Staudtian vision. He showed that the algebraic field properties von Staudt had painstakingly constructed through the calculus of Thoreau's could be derived with even greater formal rigor from a lean set of axioms. The work of David Hilbert, whose 1899 Grundlagen der Geometrie became the definitive text on the axiomatic foundations of Euclidean geometry, likewise operates in this same spirit. While Hilbert's system reintroduces axioms of congruence, its methodical separation of axioms into groups of incidence, order, congruence, and continuity reflects the same desire for logical clarity and independence that motivated von Staudt's entire career. Hilbert's project was to place all of geometry on a secure logical footing, and in the domain of projective foundations, von Staudt had already laid the cornerstone. To appreciate the full measure of his legacy, one must look past the specific theorems and constructions, remarkable as they are, to the fundamental shift in perspective he engineered. Before him, The creation of non-Euclidean geometries by Lobachevsky and Balabai had already fractured the monolithic authority of Euclid. They demonstrated that alternative, consistent geometries were possible by altering a single postulate, the parallel postulate. Theirs was an internal rebellion, a change of law within an established kingdom. Von Staudt's revolution was of a different order entirely. He changed the constitution of the kingdom itself. He refounded geometry on a new set of primitive terms, demonstrating that the familiar world of lines, planes, and conics could be built without any reference to our sensory experience of space. He completed the liberation of geometry from intuition by showing that the algebraic field of complex numbers could arise organically from axioms of connection. He sealed the union between algebra and pure geometry, revealing them as two languages describing the same abstract reality. The ultimate triumph of Karl von Staudt was to reveal projective geometry as the deep structure, the elegant and capacious framework within which all other classical geometries find their proper place. His work established a new ideal for mathematical rigor and abstraction, leaving behind a silent, austere, and breathtakingly powerful vision of a universe woven from pure relation.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.